Hello everyone, my name is Petron, and in this video we are looking at a neuroscience cheat sheet. Not for the neuroscience student, but for the interdisciplinary people. This cheat sheet, summary paper. This cheat sheet, summary paper, or mini mind map if you want to call it, is a part of a Neurotech mind map, and all of the content will be available in their ads as well. The reason that I'm making this because if you want to memorize something, it is best to have your document focus on a specific topic. Since everything here is related to neuroscience and computational neuroscience, I believe everybody will have a more intimate relationship with the content and learn it faster. There are two versions of this mind map. One is the topic and one is the extended version. They are all in the PDF format and you can use them offline. So in middle one is the extended version and the two right one are the topic one. So the app I'm using is called Xmind. It is just becoming my favorite mind map making app. Hats off to their team, it's really an amazing software. The PDF version of this mind map is available to download on my Patreon page for free. Or are they? Oh, come on, I'm just kidding. Of course, I'm gonna make them all for free. Or am I? Okay, I'm just gonna stop it. It's obviously for free. Unless, I'm seriously gonna stop it. First, we are gonna take a look at the topic version. It's good to know what is the mind map and review the content. After that, we look at the extended version of it, and finally we take a look at some PowerPoint tips on how I made these PowerPoints. And everything is timestamp. Feel free to skip in any part of the video if you want. And let's jump into it, guys. So the neuroscience cheat sheet. The left part is the different part of the brain, and there's a link to a 3D version of the brain. I highly recommend you to check it out. And the right part, we get into the more detail of what's going on the central nervous system of the brain. We take a look at the different neuron types and how we categorize them. Then you have glial cells, because 50% of the brain is made out of those glial cells. And of course, all of them will release some sort of neurotransmitter. A neurotransmitter released from neurons are called neurotransmitter, and neurotransmitter released from the astrocyte are called gliotransmitters. So these are here, and the good part about the Xmind mind map is that you can unfold and fold information, and it's really good when you're reviewing stuff. So if you're reviewing, it's best to just take a look at this version of the mind map, which they are all available in PDF format. Then we have the references, and some part of the mind map have this summary. And yeah, it's really good to have a summary of these summary information. They are all, of course, summary, but a summary from this summary would be really cool. So we have the cell biology. I don't know if we get into this cell biology too much because it's something for interdisciplinary student, and we don't really care about what's happening in the neuron. We just want the essence of information. But if you want to know what's going on, there's a video from Ninja Nerd YouTube channel. It's a really good one. I will add it to the mind map whenever I have the time. And after that, we have electrochemical behavior of the neurons and what's happening here. So we have different part of neuron and different kind of channels that are on the neuron. We take a look at them. Then we look at how action potential is happening. And one thing that not a lot of people talk about it is how bursting is happening. I will not get into so much of detail on how bursting is happening. I will leave it for the next time. Then we have a summary part of these sections, and in the reference part, I highly recommend you to check out these videos that I labeled, because you need to watch those first to understand what's going on here, to understand the summary of what's going on. So yeah, So after that, we have activity levels and some concepts that are happening in the brain. I haven't really invested so much of time on this part. I just know that we have some microscopic and macroscopic point of view. So yeah, we better first understand what's going on in the neuron level, and so we can then understand what's going on in the network level of these neurons. So speaking from the neurons behavior, we have some category about how many activity and how many type of spikes they make. I categorize them here. So the first part is based on the reason that they make, and the second part is just the repeat of what's happening top here, but regardless of the reason. This part is still under development, so yeah, the main part is up here. Then we have so much information in the extended version. All right, we have some mathematical analysis. Neuroscience people really love some mathematical analysis, and the most important one of them is bifurcation analysis. We check it out in the next version. And we have now entered into computational neuroscience region, which we take a look at some computational and modeling aspect of these concepts that we already watched, because after all, our main goal is to model. All right, so we have neuromodeling. The reason behind some of these: astrocyte modeling, tripartite synapses, and different type of networks. I have some really good figures about different type of neurons here. All right, so this is an overview of what we are gonna take a look at right now. Now let's get into more details on what's going on here. So starting from top here, you can see some links to the social media that I have, and a link to this mind map on where you want to download it. The link to this video will be available here that I'm moving my cursor, and the latest version is here. You can see what's going on here. So entering the nervous system has is made out of central nervous system and peripheral nervous system. Central nervous system is explained in detail in the left side here, and if you want to know more information about it, I highly recommend you to check this website, which is a 3D version of the brain. But looking at this part, this figure here is the brain and spinal cord, which is the central nervous system. It has some different parts. It's not necessary for interdisciplinary student to know exactly which part is doing what, but it's not to know actually what's happening here, because for example, you're studying something in hippocampus, you should know where it is and what it is doing, not what's going on here. So there's two references here, and one of them is a book. I copied the figure from this book, and there's a link to a video. He talks about 19 main parts of the brain and what they do. I have a mini summary of what's happening in that video here, but I highly recommend you to check that video. He just talk about different parts and what are their roles and review them for you. And yeah, it's a really good one if you want to actually understand what's going on. Yeah, moving on, the nervous system. So as we just talked about it, the nervous system is made out of central nervous system, which is the brain and the stem, and we have a peripheral nervous system, which is really actually related to anatomy of the body. So if you want to know more about these parts and what they do, I highly recommend you to check Crash Course Anatomy and Physiology, and a good part of that they will talk about this central nervous system, different type of neuron and how what they do. I will add more figure to this mind map later on the next version. So we have neurons and morphology and category of the neurons. Top here, based on the function of neuron, they are categorized into three types. We have sensory neurons, motor neurons, and interneurons. Sensory neurons get information from the outside. Motor neurons just order your organs to do something, and interneurons just communicate in the brain. So this is a very basic definition of what neurons are, how neurons are categorized. And if we want to categorize them based on the morphology, they are categorized into 4 main groups: unipolar, which is this one, bipolar, pseudo-unipolar, and multipolar. There are of course more types of these neurons, but those neurons are usually they have lots of dendrite, which are these parts. These are the parts. These parts are called dendrite, and the newest version of these neurons, as far as I know, is called rose shape. They discovered it in 2018, and I saw its figure, and it's kind of similar to these two. They have lots of dendrite around them. So yeah, so looking at these, the different part of the neuron, these parts are axon. These terminal are called dendrite. We have the cell and we have the axon terminal, and yeah, let's check them out. And based on their morphology, they have different parts and they do different activities that we will look at them in the further parts. So we have this one is called pyramidal cell. It has 3 parts, three versions: CA1, CA2, and CA3, which the difference between those 3 versions are the number of dendrites that are here. So each one of them can have different category like that, which you can always search about them on Google Scholar and see the latest review paper about them. All right. Moving on, we have glial cells. Glial cells in central nervous system and peripheral nervous system have different types. Most important one of them, let's say, is astrocytes. If you want to know more about this, just search about them on the net and you find a video from Ninja Nerd YouTube channel. He explains it really well on what's going on. But basically what astrocytes do is they communicate with each other via the gap junction with IP3. These glial cells don't make action potential. Only neurons make action potential, and these glial cells will affect them. So we have morphology of neurons. They are dendrite, cell body, and we have axon. Axon has different parts. Axon hillock is the opening part of the axon. Again, I will add more figure to these parts, but just know about them right now. We have myelin sheath, which they're wrapped around the fiber. They're wrapped around the axon. They make the action potential happens faster, and there are some nodes of Ranvier between these myelin sheath. And these axon terminal, which is the tip of the axon, they can be attached in 3 other manners. They can attach to other axon, they can attach to other dendrite, and they can attach to the soma of the other neuron, which the most abundant form of them, I think, it's attached to the dendrite that we most of the time consider when we are modeling the neurons. So these synapses can be electrical or chemical. Good information about them is available on the crash course when they are talking about the nervous system. So we have neurotransmitter. I just brought some of the most important one of them here, but actually we use only 2 of them. 2 of them we use most often. One of them is glutamate, which is the excitatory, which is the most abundant excitatory neurotransmitter, and another one of them is GABA, which is the most abundant inhibitory neurotransmitter. And what I mean that if these neurotransmitter release after the action potential happen, so after the action potential happen, these neurotransmitter will be released in the synaptic cleft, which is a place that 2 neurons are connected to each other. And again, I will add more figures about them. And if they release glutamate, they excite other neurons. It makes them more probable that they fire the postsynaptic neuron. And if they release some inhibitory neurotransmitter, they make the postsynaptic neuron less probable to fire. We have also ATP, which I didn't brought them here, but I might update this list later on. So yeah, moving on to the next 2 version, where we take a look at how these neurons make action potential. So we have the cell biology. I'm not sure if I get into it, but check this video. So this arrow that you can see, this is a link. If on the PDF format, if you click on it, you can access the link. Yeah. So the electrochemical mechanism of neuron. So there are different type of ion channels. There are different type of ion in the neuron. And what makes them to do action potential is that something happened, these ions flow in, and because the inside of the neuron has more negative ion than outside of the neuron, so inside of the neuron is less positive than outside of the neuron, and we just call it the inside has some negative charge. But this negative charge is much different than the negative charge in our electronic devices. So before explaining these currents and the ions, let's take a look at how action potential is happening. I wrote completely here in detail on what's happening here. I wrote it from this video here from the Harvard Extension School. Watch this video, but this is a summary of what they say here. And I have a figure here that we can take a look at this. So the resting potential is most of the time minus 70 or sometimes minus 65, and then some things happen, and the sodium channels will open here, and it wants to rise, and the potential wants to rise. If this one passes the threshold, the action potential will happen. So the sodium ion will flow into the neuron, and it peak, and we just call it the neuron is depolarized. So we call it is depolarized because it was negative and the negative charge is out. This concept was a bit confusing to me because I'm an electronic engineer and we just work with positive charge, and whenever we say depolarize, we mean that if something had some positive charge and now it's just releasing some positive charge and going to the zero direction. So whenever the voltage is going through the zero, it is depolarized. It is rising now, but it is going through the zero, and it peaked at plus 30, but we call it depolarized because it's just releasing its negative charge. It's releasing its charge, and at the peak the sodium channels will be inactivated, and we have the potassium channels coming in. So this part is called absolute refractory period, which is something that useful. So after the sodium ions come inside of the neuron, these channels will be closed, so to determine the direction of the action potential. So the action potential should go through the axon to the axon terminal. We don't want it to go through the soma. Although sometimes some stuff will happen that two action potential will happen, which we will take a look at this in the next part. So the sodium channel will be closed, the potassium channel will be open, and we are polarizing again. Because these potassium channel are slow to close, we have some after hyperpolarization, and the whole time we have some sodium potassium pumps which are on, and after around a point minus 90 millivolt, these potassium channel will be closed, and the neuron waits to get back into its resting potential by the sodium potassium pump. So this part and this sodium potassium pump actually determine when the next spike should happen. This is a really important one thing that you should remember. And they just get activated by ATP, and they bring the sodium out to potassium. Alright, so this was a quick summary on the action potential, but you cannot find anything on how they burst. So we have on the internet, so actually knowing how they burst is important, which we have some channels here. You can see the calcium channel and chloride channel. I haven't talked about them yet because they are affecting the neuron in a way that when they want to make burst. So yeah, I'll talk about bursts in the next episode because there are a lot of details that we should know before we get into the bursting. So we have the sodium channel here. There are different type of them. I put a link to a Wikipedia page, and you have the potassium channels here. This potassium channel, one of them is delayed rectified, which is the main potassium channel that we just see that it will be activated. Another one is after hyperpolarization potassium channel. It will be activated then. Another one is related to the calcium, which it relates into the bursting behavior of the neurons. And there are two other models which, if we want to model our neuron more exact, we just add them into the equation. But most of the time in single compartment neuron, they use the first one and the second one, maybe. And if we want to describe burst, we have this third one. All right, you can study the information here. Put a link to its reference down in the section. We have some more definition here. These ions was flowing in and out because of the electrochemical gradient. It's just beautifully explained in that Harvard School extension video. Just watch that. It's just really cool one. And the one thing they none of them talk about this, both Crash Course and that Harvard School, is the neural back propagation. It's a really cool feature of that neuron has. So whenever they make an action potential, sometimes this action potential happens in the dendrite, and this is called the echo of action potential. So I put a link to its Wikipedia page. You can just study this. It's explained very beautifully, but it's the main reason behind the ping-pong behavior between the axon and dendrite. These terms might be a bit confusing if it's first time that you're listening to them, but after watching these videos that I linked them, check out this one. This is something that's really cool. Not gonna study about it. It's actually effective in the bursting behavior of the neurons. So yeah, and to summarize it, we have the type of channel up here, and we have the actual channel of sodium, potassium, and stuff like that here. In the second part, I have some other definition at the bottom of this part, and I just summarize what's happening in the action potential in this section, and the bursting will be added in this part. And of course, a summary for this one, like this, that you can see for action potential will be added here for the bursting. There are more references here, check them out, they are really cool. And we are moving into the next two sections. So the activity levels, we have macroscopic and macroscopic. So you have to understand what's going on in the neuron levels, which is actually next part that we take a look at the behavior, different behaviors that neuron can make. So if we just take a look at the neurons by themselves, they can either spike or burst. There are different types of spikes and burst, which there's an amazing figure on the EasyCapich website. You can check it out here. Yeah, these are the different behavior that you can see from the neuron, and actually his equation is explaining these behavior as well. So yeah, his model is really widely used to this day. So after that, other stuff is affecting how these neurons behave. So these are the models that we are making from the actual neurons. So if you just have some single compartment neuron or multi-compartmental neuron, we can have them like that. They will show behavior like this. We have some figures about these compartments that I'm talking about, but also other neurons can affect other neurons as well. So here there's a figure from a video from the Khan Academy. So we can see a neuron is here and an excitatory and inhibitory neuron is connected to it. So some type of behavior can be seen in a train of action potential instead of just some action potential. So if you have a train of action potential and an excitatory neuron come here and just excite this neuron, we can see some behavior like that, as opposed when we had no train of action potential, we couldn't sense this activity. We might just see that it's some type of bursting, or at the bottom of here. Yeah, these are some other type of activity that we might expect from the neuron. And there's another one. So glial cells can highly affect how neuron can behave. Astrocyte is one of the most important one of them. And yeah, I will add more information about them. I've got some good information about them, but they're not organized currently. So at the bottom, as I told you before, there will be the behavior of neuron regardless of their reason, and yeah, it's still under development, but they will be finished hopefully in the future model. So we have mathematical analysis. So something neuroscience people really love is the bifurcation analysis. There's a video from the Vertassium YouTube channel. Watch it so you understand what's actually bifurcation. And there's a review paper from the Zikovich. It's around 100 pages, and it will go into deep detail of how they do bifurcation analysis. I recommend you these two if you are new to this concept. Alright, we have the last part, which is the most exciting part, and the actual modeling is just happening here, and all we studied and took a look at is just connecting here. So different type of modeling happens because we do different type of approximation, and the most common of them is perceptron based, which is not actually a part of computational neuroscience and spiking neural networks. It is just something that computer people, IT people love to use it, and all the deep learning and artificial intelligence that we have is based on this perceptron base. So yeah, this is this. And then we have single compartmental, multi-compartmental, and cable model. There are some good figure about them here. As you can see, the left figure is the perceptron base, which we have the perceptron, and we have the synaptic connection and their weights here. So yeah, the basic deep learning is just synaptic weights and input, layer, output, and stuff like that. But we are just dealing with the real neurons, and we want to model these real neurons. And the way we approach to them is that we first do some cable model like this. Then we define different compartment for them, and then this different compartment will turn into mathematical model. So there are some electronic circuit from these. They are called cytomorphic circuit design, but we have neuromorphic circuit design. The cytomorphic is just dealing with what's happening in the cell and the DNA, and the neuromorphic is dealing with the electronic properties, the action potentials and stuff like that. So yeah, these are the compartmental model. So in neuromorphic and cytomorphic, that we actually make chips. We are not making from these resistor and capacitor. We just make them with the CMOS transistors, which is actually the beauty of the work. All right, moving on. So yeah, these cable models and multi-compartmental models. Each one of them is good in something. You can study this part. In the reference is provided here down this part. I'm just skipping this part. Then we have neural modeling. So we have different compartmental. We have main currents. So what we want to do, we have pulling conductances between the compartments. Whether we want to actually model the neurotransmitter that are happening here. So this part is still under development, but the part that I will talk about in detail is the network of the neuron. So based off the connection and the type of neuron, you have different type of networks. But before going to the network of neuron, let's take a look at the astrocyte. So when we have a presynaptic neuron and postsynaptic neuron that they are connected to each other, there's an astrocyte between them in the gap junction here. It can affect what's happening here. So these neurons communicate with each other via neurotransmitters. So when they release neurotransmitters, someone should reuptake this neurotransmitter and bring them back to the presynaptic neuron or postsynaptic neuron. and put them into the vesicles which they were initially, and make them ready again for another action potential. So yeah, this is the reuptaking that's happening by the astrocyte. So the presynaptic neuron fire, for example, glutamate is released, glutamate go into the astrocyte, is glutamate turn into IP3, and then IP3 go into the ER, which is endocannabinoid reticulum, this is the abbreviation of this, and then it will release some calcium, and this calcium will turn into some glutamate, and this glutamate just turn back into the presynaptic neuron and postsynaptic neuron. A detailed explanation of this, I will add some more reference to the detailed explanation of this, but a good explanation and basic of it is available here with a reference to the article that I provided here. So yeah, you can check them out here, and yeah, definitely read them, they're really cool. So for the network level, we have network of neuron, network of astrocyte, and neuron astrocyte interaction. So network of neuron, they can be 1D, single dimension, 2-dimension, and they can be connected to each other in linear fashion or exponential fashion, which is distance dependent. So the figure that you can see here, the presynaptic neuron is connected to postsynaptic neuron, interneuron, pyramidal neuron, and there's the astrocyte here, and you can see the tripartite synapses happening here. This presynaptic neuron connected to postsynaptic neuron, and the astrocyte is monitoring this connection among these two. And astrocytes are connected to each other in a linear fashion, 1D, and neurons are connected to each other in a linear fashion, 1D. So if you want to make it more complicated, you can see in the next figure that the neuron layer is 2D, the astrocyte is here, they are connected to 4 neurons, yeah, but still the neuron astrocyte interaction is proximal, which means that this astrocyte is just monitoring the connection around it. So the next one, which is the most advanced one of them, is this one. So this layer is input layer, this one is neuron layer, and the other one is astrocyte layer. Astrocyte layer are connected to each other in a 2D fashion. Neuron network, on the other hand, are connected to each other in an exponential fashion, like this, and their synaptic weights is dependent on the distance that they have. Yeah, so they are 2D, exponential. I wrote it in a linear is wrong. They are exponential. The astrocyte network is 2D, but the neuron astrocyte interaction is just monitoring a region of neuron instead of just monitoring a few neurons around it. This regional and exponential, I just said it from myself. I feel like it's correct to call them like that, but they might not be correct to call them like that. Alright, you get the deal on what's going on. So that's it. Alright, I hope you enjoyed it as much as I did explaining it. This is the extended version and this is the topic version, and they are all available on my Patreon page. You can download them for free, and they are a part of the Neurotech mindmap. Before ending it, let me give you some tips on how to make a slide like this. So if you have the Xmind app, you can make them here, and you can export this mindmap in a PNG format. So after you export them, you can either export them in a PNG format, or you get a screenshot from them with another app called Snagit. You can just use a Snagit and get a screenshot. So after you export these figures, you cannot just copy and paste them here, because if you do, the resolution will be screwed, and you can just use anything. You can just use the figures. So you have to open them with the Snagit, then copy them from the Snagit. For example, if you're here, just copy them from here, like here, right click and copy them from here. After you copy them from here, if you paste them here, then they will be fixed if you add any transition to them. So in order to make slides like this, you have to put the figure here and just zoom in like this and make the transition into morph. So if you do that, as you may already seen what's going on, stuff like this might happen. So we have next slide, but it is blurred like that. In order to fix it, I'm currently using Office 2021. You have to add the same slide. That means you just duplicate that slide and just add no transition, because after they do that, if the PowerPoint don't just render the figure again to save the quality. So yeah, that's the tip that you need to know about it. All right, see you guys next time.